In this video, I'm going to explain the theory behind clock reactions and how we can use this experimental method to measure the initial rate of a reaction. I'll also show you how to calculate the percentage of the reaction being studied. So, let's make a start. For any chemical reaction that we're studying, we can measure the increase in concentration of product over time, and we can plot that on a graph. If we do so, we end up with something that looks a bit like what I have here. We have got concentration of product on the y-axis. Remember that square brackets denote concentration, and time on the x-axis. And we can see that at the beginning of the reaction, we make our product very quickly because we have plenty of reactants in the system, but over time the amount of product that we produce levels off. Eventually the reaction runs out of reactants. And if we draw a tangent to the curve at t equals 0, we can calculate our initial rate of reaction, which is change in y divided by change in x, change in the concentration of product being formed divided by the time taken to form that amount of product. You'll also notice that for the first, say, 15% of the reaction time, the initial rate of reaction doesn't actually change. Another way of looking at it is that if we measure the time taken to produce a certain amount of product, or perhaps use up a certain amount of reactant, then the quicker that happens, the faster the reaction must be happening. So T1. If I increase the concentration of my reactants and repeat the experiment, I would expect to make my product faster, in which case the time taken to reach that particular concentration of product, we'll call that T2, is much shorter. So what this means is that we can take 1 divided by time as a relative measure of the initial rate of reaction. The trick, of course, is knowing when we've produced that fixed amount of product. Let's take a look at this reaction between peroxide disulfate ions and iodide ions. This is an example of an iodine clock reaction because, as you can see, the reaction produces iodine. Now, the easiest way to measure the rate of this reaction is by following the colour of the iodine as it's produced. But in dilute solution, it's a kind of pale yellowy brown colour, so it's really hard to distinguish when we've made a fixed amount. However, if we add some starch to our reaction mixture, then as the iodine is produced, it reacts with the starch to form a blue-black complex, and this is very easy to spot. Now, we can measure how long it takes to produce a small fixed amount of iodine if we also add some sodium thiosulfate to our reaction mixture, because thiosulfate ions, and not to be confused with the peroxide disulfate ions in our actual reaction mixture, but our thiosulfate ions react with iodine and they reduce it. We get some of these S4O6 ions and iodide ions. Iodide ions, of course, are colourless. The iodine that it's produced in the reaction between iodide ions and peroxide disulfate ions, and this of course is the reaction that we're following that we want to measure the rate of, the iodine that's produced reacts with the sodium thiosulfate until all the sodium thiosulfate is used up, and then, hey presto, the next molecule of iodine forms the blue-black complex with starch, and we can start the stop clock when we put our reaction together, and we can stop it the minute we form this blue-black complex. The faster we see the blue-black complex, the faster the rate of reaction. In practice, the reaction is very, very straightforward to run. We would place our peroxide disulfate ions into a test tube. We would place our iodide, our thiosulfate and our starch into a conical flask. We could measure out these volumes, say using a burette, to make life nice and simple for ourselves. The minute that we pour the peroxide disulfate ions into the reaction mixture, we start the stop clock. And the minute that we see the blue-black complex form, we stop the stop clock. And so the time taken to produce this starch iodine complex gives us a relative measure of our initial rate of reaction. Now, that's fine, we'll have one value then. What we would then need to do is to repeat this experiment, changing the concentration of the potassium iodide, so we can see how the rate varies dependent on the concentration of iodide ions. When we do that, we get a set of results that might look a little bit like so. Concentration of iodide ions is falling with each experiment that we carry out. As you would expect, we'd expect the rate of reaction to slow, and that's what we see. The time taken to form our blue-black complex increases, and then our initial rate of reaction is simply 1 divided by the time. So 1 divided by 80, 1 divided by 105. Some of you may have noticed that my iodide concentration here I've got down as 0.5 as my strongest, and yet when I was showing you the method, I had an iodide concentration of 1 mole per decimeter cubed. Why the discrepancy? Well, the 1 mole per decimeter cubed is the concentration of potassium iodide measured out of the burette and placed into my reaction mixture, but this is 5 centimeters cubed out of a total volume of 5, 6, 7, 8, 9, 10 centimeters cubed. So the actual concentration of iodide ions in this reaction mixture is 5 divided by 10 times 1.0, which of course comes out to 0.5 mole per decimeter cubed. So repeating this experiment, maybe I would add 4 centimeters cubed and 1 of water, 3 and 2 of water, and so on to change my initial concentration. In order to find the order of reaction with respect to iodide ions, I would then plot a graph of concentration of iodide ions against 1 over T. And remember, 1 over T is a measure of our initial rate of reaction. And when you do that, we can see that we get a straight line passing through 0. We have a proportional relationship between the rate and the concentration of iodide ions, which means it's first order with respect to iodide ions. If I wanted to know what the order is with respect to peroxide disulfate ions, then I would repeat that set of experiments, but instead of changing the concentration of iodide ions, I would change the concentration of peroxide disulfate ions each time, keeping everything else the same. The final thing we need to be able to do is to work out the extent of the reaction that's being studied as a percentage. In order for our clock reactions to be vaguely accurate, we want to be studying less than the first 15% of the reaction, where the initial rate of reaction is pretty steady. So how do we go about that? Well, it's actually fairly straightforward. Step number 1, we need to determine how much iodine is made in our reaction. In order to do that, I need to know whether the peroxide disulfate ions or the iodide ions are our limiting reactant. So let's start with our peroxide disulfate. Well, to find the amount, the number of moles, so the number of moles of the peroxide disulfate is equal to our concentration times our volume in decimeters cubed. So our concentration, if we go back, was 0.04 mole per decimeter cubed, and this is all on the little picture I have of my method. So 0.04 mole per decimeter cubed, and the volume was 2 centimeters cubed. Well, 2 centimeters cubed is 0.002 decimeters cubed, so that comes out as 8 times 10 to the minus 5 mole. The ratio of peroxide disulfate to iodine is 1:1, which means that we would also make 8 times 10 to the minus 5 moles of iodine. Let's check for iodide ions. Well, number of moles of the iodide ions once again equals concentration times volume. Well, my concentration was 1.0 mole per decimeter cubed, and my lowest volume would have been 1 centimeter cubed. So I start off with 5, then 4, then 3, then 2, then 1. So that's 0.001 decimeter cubed. So that comes out as 1 times 10 to the minus 3 mole. Now, I should probably have done this in a different colour. So 1.0 times 10 to the minus 3 mole. The ratio of iodide ions to iodine is 2:1, which means that the amount of, or the maximum amount of iodine that I could have made would have been 5.0 times 10 to the minus 4 moles. What does that tell me? Well, it tells me that the peroxide disulfate is my limiting reactant. I can't make more iodine than 8.0 times 10 to the minus 5 moles because I will have run out of my peroxide disulfate ions at that point. Step 2 is to determine the amount of sodium thiosulfate present, because if I know how much thiosulfate I've got present, I can figure out how much iodine was used up in the clock, the time before my blue-black complex was formed. So, to find the number of moles of sodium thiosulfate, once again, exactly the same, number of moles equals concentration times volume. Concentration was 0.01 mole per decimeter cubed, and we added 2 centimeters cubed, 0.002 decimeters cubed, so the number of moles is 2.0 times 10 to the minus 5. The ratio of sodium thiosulfate to iodine is 1:2, as it's written in this equation, or 2 thiosulfate to 1 mole of iodine, which means that the maximum amount of iodine that was used up in every clock, i.e. that was produced before the blue-black colour formed and we stopped our stop clock, would be half that. So number of moles of iodine used up in the clock part of the reaction is 1.0 times 10 to the minus 5 moles. So at this point we can work out the percentage of the reaction studied, because we know how much iodine was produced before the blue-black complex formed in each case, and we know the total number of moles of iodine that could be produced in this particular reaction. So it's going to be 1.0 times 10 to the minus 5 divided by 8.0 times 10 to the minus 5 times 100, and that comes out at 12.5%. So we've been studying the first 12.5% of this reaction. As always, if you check the blurb below, there is a link to the Crunch Chemistry website where you will find notes for this video, some practice questions, and also some other examples of clock reactions that are commonly used in exam questions that would be good to be familiar with. At A-level, particularly in this kinetics topic, it is really important that you understand how the experiments and practicals that we do in the lab actually relate to the theory, how we can turn methods into results, analyse those results graphically, and then come up with information such as orders of reaction and the rate equation. If this has been helpful to you, then please hit the like button, subscribe and share. It makes a huge difference to a small channel like us. I look forward to seeing you next time.